Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
It's a pleasure to welcome Sergey Levine. This is actually the second time we're trying to recruit him. The first time was when he was applying to graduate school, and he went to Stanford instead. But young people sometimes make that mistake. It's understandable. At Stanford, he worked with Vladlen Koltun on graphics and animation and control techniques for complicated characters, and has done lots of exciting work. He also had some connections with Zoran Popovic and colleagues here. Then he moved on to Berkeley, where he's now a postdoc in Pieter Abbeel's lab, and he's applying his techniques to robots such as the PR2 and getting it to do exciting things. And he works at the intersection of graphics, machine learning, and robotics, and he's doing really exciting things in all three of them. And these are all hot areas that it's really good to see them coming together. So it's going to be a very picturesque and exciting talk. Thank you.
Thank you, Emu. OK, so my name is Sergey Levine, and I'm going to talk about deep learning for decision-making and control. Decision-making and control problems come up in a range of different fields, from operations research to economics, even to things like educational games, as well as continuous control tasks like autonomous vehicle control, character animation, and robotic manipulation. So in this talk, I'm mainly going to focus on continuous control tasks, although I'll come back to some broader applications at the end. So let's start off with a video. This is a robot participating in the DARPA Humanoid Robotics Challenge trials held last year. This is a team from Lockheed Martin and the University of Pennsylvania. And although this robot is constrained to some degree by the parameters of the contest, this was a very successful team. They actually placed in the top 10 in the competition. And here the robot is trying to open this door. But it's a little hard to watch a video like this and not be a little disappointed. From the point that the robot is positioned in front of the door to the point that it gets it open is about 1.5 minutes. I asked a colleague of mine at Stanford to try this task, and here's how he did. Now, you might say that, well, he's using his really awesome binocular vision, hand-eye coordination to do this task really fast. But in fact, if we zoom the camera out, we can see that he's doing this task blind. So what's going on here? Why is Philip here so much better at this task than the robot? Well, to begin to answer this question, let's look at a different task, one that has been studied in a bit more detail, the task of catching a ball. Evolutionary biologist Richard Dawkins wrote that when a man throws a ball high in the air and catches it again, he behaves as if he had solved a set of differential equations in predicting the trajectory of the ball. And at subconscious level, something functionally equivalent to the mathematical calculations is going on. So was Richard Dawkins right about this? Is this actually how people catch a ball? Well, it turns out that the answer is no. In the 90s, scientists actually studied this question and came up with a very different answer. We actually do something very simple. We use what's called the gaze heuristic. We look at the ball, and we fix its position in our field of view, and we begin running. And we actually adjust our running speed so the ball stays in the same position in our field of view. And if we follow this very simple sensory motor heuristic, we'll actually arrive at exactly the place where the ball lands. So by short-circuiting this complicated pathway from perception to control, we can actually come up with a very simple rule that's going to be robust, and it's going to work in a wide variety of situations, and it avoids the need to do all that complicated modeling to estimate the ball's velocity, wind resistance, and so on. So the aim in this talk will be to develop algorithms that can learn these kinds of sensory motor skills. If we can learn these kinds of sensory motor skills automatically, we can endow robots with large repertoires of behaviors that can allow them to succeed in complex real-world situations. For example, we can develop household robots that are equipped with a range of different behaviors that allow them to perform chores in your home. We can endow robots built for disaster relief with a wide range of skills that they need to succeed in complex environments with unexpected perturbations. But we need to develop algorithms that will actually learn these kinds of sensory motor skills if we want this approach to scale. So we're going to draw on ideas from 3 different fields to develop these methods. The first is optimal control. Optimal control is concerned with choosing a sequence of actions that minimizes some cost function. The cost function is a measure of your task performance. There have been a lot of advances in optimal control methods in recent years for things like trajectory optimization. You can roughly think of this as planning. For complicated tasks like locomotion with contacts and so forth. Optimal control methods are very general, so they can be applied to a wide range of tasks. But in optimal control, nothing is learned. So solving one optimal control problem doesn't make it easier to then go and solve another one. And furthermore, optimal control doesn't tell us anything about how we should deal with perception. So if you want to apply optimal control, you first have to do state estimation. You have to figure out the position of the ball and its velocity before you can plan a path that will go and catch it. Now, the area that's perhaps more directly concerned with learning sensory motor skills is reinforcement learning. And in reinforcement learning, we're also aiming to optimize some cost function, but now we're going to try to choose the parameters of some policy that will give us an action in every state such that this cost function is minimized. Reinforcement learning has been applied to a range of tasks, from inverted helicopter flight to bipedal and quadrupedal locomotion, and also to robotic manipulation. But many of the most successful applications of reinforcement learning have actually relied on a combination of learning and manual engineering. So typically, what we would do in previous work is actually manually design some controller class. For example, for bipedal locomotion, this controller class might capture some notion of balance. And this controller would expose a modest number of parameters that are then optimized from real-world experience. So the advantage of reinforcement learning is that we're going to have learning and generalization, but the disadvantage is that we typically need to hand design the representation for what we're going to learn, and we're quite limited in the number of parameters that we can learn because these methods are so difficult to apply to high-dimensional policies. The third area from which we're going to draw on for ideas is deep learning. Deep learning has achieved a lot of state-of-the-art results recently for perception tasks like vision and speech recognition, but has not been extensively applied for robotic control. So I'm going to illustrate the main idea behind deep learning with a vision example, and then I'll talk about how we can apply it to robotics. So in a standard computer vision pipeline, we might begin with pixels in an image. We might extract some low-level features from this image, like a histogram of oriented gradients. We might then extract some mid-level features, like a deformable parts model, and then build a classifier that actually detects the thing that we care about. In deep learning, we're going to do all of the same things, except that each stage in this pipeline, each of these feature layers, is actually going to be learned from the data. By learning all of these features from the data, we can actually adapt our representation to the task, and this also dramatically reduces the burden on hand engineering because we don't have to manually design our representation. The key, of course, to this is that we have to supply the learning algorithm with a sufficiently expressive function for it to learn that can represent all of these many layers. So where are we at with robot learning? Well, the standard robot learning pipeline might look something like this. We start out with some observations that might include, for example, images from a camera. We do some state estimation, which would include things like vision. For example, we might localize the position of the ball in the image. Then we have some manually designed policy class that exposes a modest number of parameters that are actually learned from experience. And in turn, they drive some low-level controller, like a PD controller, that actually chooses the torques on the robot's joints. Our aim with deep sensory motor learning is going to be to actually learn the functionality of each of these stages with a single function approximator that's sufficiently expressive to capture whatever functionality is necessary there to map directly from raw observations to the motor torques at the robot's joints. So what we're going to aim to do is to learn a general-purpose neural network policy. The main point here is not that it's a neural network. The point is that it has enough parameters and is sufficiently expressive to capture the kinds of interesting parsimonious relationships between input and output that we care about, like the gaze heuristic. Formally, the task consists of optimizing the parameters of this neural network in order to minimize the expectation of the cost of the task. So the cost is a function of the state of the system, which might include, for example, the joint angles of the robot, and the actions, which might be the torques at the robot's joints. The policy gives us a distribution over actions, those are the torques at the robot's joints, conditional observations. And the observations may or may not be the same as the full state of the system, so it might include things like camera images. Now, if we open a textbook on reinforcement learning and we look up a standard way of solving this kind of problem, we might see a method that looks something like this. Take your current guess of the policy, run it on the robot to generate samples. Some of these samples will be good and some of them will be bad. Then take the good ones and make them more likely, and take the bad ones and make them less likely. And this is a very sensible and simple approach to improving the policy. Unfortunately, it starts to break down when your policy is extremely high-dimensional. So let's try to illustrate this with an example. Let's say we want to learn a neural network policy for bipedal running. There's definitely a neural network that can do bipedal running. In fact, I'm going to show you one in just a few slides. But if we initialize the parameters of our controller at random, we're not going to get bipedal running initially, we're going to get bipedal falling. And applying this kind of reinforcement learning strategy basically amounts to falling repeatedly until you happen to accidentally run and then try to run more and more often. So this is an event with very low probability. So trying to use this approach to learn running with such an expressive representation is going to be impractical. So in this talk, I'm going to introduce a class of algorithms called guided policy search that aim to bring in concepts from optimal control to make this problem tractable. I'm going to then describe how guided policy search can be applied to tasks where we don't know the dynamics of the system, which is going to be very important for robotics. I'm going to talk about how guided policy search can be used to learn policies that directly map from raw vision input from images to the torques at the robot's joints to learn visuomotor policies. And then I'll talk about future directions and how we can go about scaling up robot learning to the vast range of motor skills that we need for practical applications of these techniques. So let me start off by describing guided policy search. To better understand the limitations of policy search with reinforcement learning, we can view it as trying to solve two very difficult problems at the same time. It's trying to deal with the complex dynamics of the task. This includes things like inertia, frictional contacts, under actuation, and also maybe partial observability. And at the same time, it's trying to deal with the complexity of the policy, which includes high dimensionality and nonlinearity. Solving these two problems together is quite difficult. However, if we have an oracle that tells us exactly which action to take in response to every observation, we can actually forget entirely about the dynamics. All we have to do is learn to mimic the oracle. And this is a comparatively much easier problem. It's basically supervised learning. You can think of it as regression, a kind of nonlinear least squares. There are standard ways of solving these kinds of problems, and in fact, this is the approach that's most popular in standard deep learning methods. But where do we get the supervision? How do we know which actions to take in response to which observation? Well, that's where optimal control is going to come in. So we can use optimal control to deal with the complex dynamics of the task without having to worry about the policy. Because as I mentioned before, in optimal control, nothing is really learned. So we're going to use optimal control as the tool to provide us with supervision. And this is also comparatively much easier. So the key idea behind guided policy search will be to take a few initial states of your system, run trajectory optimization, an optimal control technique, to figure out how to solve the task from those initial states, and use these solutions to generate supervision so that we can optimize our neural network policy with supervised learning. So the key thing to take away from this slide is that the aim of guided policy search is going to be to decompose this complicated problem of policy search into two easier problems, trajectory optimization and supervised learning. And for these two subproblems, there are good standard solutions that we can use. Now, unfortunately, if we try to just apply this method naively, it's not quite going to work. If we optimize a trajectory and then we solve a regression problem to get the policy to try to match this trajectory, the policy is going to make some small mistakes. And as soon as it makes a small mistake, it'll find itself in a state that's a little bit different from any of the states seen during training, and then it'll make a bigger mistake. And these mistakes will compound until eventually your policy ends up doing something totally different from what your trajectory did. So this by itself is not quite going to work. Now, we can mitigate this problem to some degree by using a trajectory distribution. You can think of this as a kind of tube through trajectory space. If we can somehow get our hands on a trajectory distribution, we can draw samples from this distribution and use those samples to train our policy. Now, when the policy makes a mistake, there will be other samples that will have made similar mistakes, and they will show the policy how it can correct itself to return back to the mean of this distribution. So this is going to be one of the ingredients in this method. How can we construct these distributions? Well, we can write down an optimization problem. We're going to solve for the distribution P of tau. Tau is a trajectory, P is the distribution. We want a distribution that contains trajectories of low cost. So we want to minimize the expectation of the cost under this distribution. But this is not enough by itself, because the solution to this problem is a distribution with exactly one trajectory, the optimal one. So this is not really all that useful to us. So we're also going to ask this distribution to maximize entropy. This is like saying, find me the widest distribution you can that only contains good trajectories. And this is going to be a good distribution for us to train our policy on. We can solve this kind of maximum entropy optimization approximately using a method based on iterative LQR. You can think of this as similar to an extended common filter. To perform this operation, we need to know a local linearization of the dynamics. So this is the derivative of the next state with respect to the current state in action. And using this approximate method, we can end up with a Gaussian distribution over trajectories. OK, so this is a tool that we're going to use. And we can use this tool to describe a basic version of guided policy search. We start out with some trajectories that are initialized either at random or perhaps from an example demonstration. We solve this maximum entropy optimization to get trajectory distributions around each of these trajectories, sample from these distributions, and use these samples to train our neural network policy with regular supervised learning, standard techniques. Using this approach, we can obtain a policy for something like bipedal running on uneven terrain. But this is not quite enough by itself to solve all the problems that we care about. And here's an illustration of why. Let's say we want to learn a policy for a simple swimming snake task. Here's a video of the swimming snake. If trajectory optimization produces a nice regular swimming gait like this, it's very easy to find a neural network that will reproduce this gait. But if trajectory optimization produces a very jagged gait like this one, now there's actually no neural network that will reproduce. In fact, there's no function at all that will reproduce this behavior because the mapping from states to actions is one to many at different time steps, but in similar states, the snake takes different actions. Now you might say this gait on the right is just a bad gait. Well, it turns out that it actually has about the same cost function. These two gaits have the same cost function. So what makes it worse is not that it's a bad gait, it's that it's less well suited for training our policy. Here's another example. Let's say we want to do a peg insertion task, but we want the policy to be able to insert the peg into the hole at any position. So we want to actually search for the hole by searching up and down the wall. No amount of trajectory optimization is going to get you the searching behavior because you're going to optimize your trajectories in a fully observed regime. So regardless of where you put the hole position, the trajectory will always go straight for the hole. So in both this case and in the case of the swimming snake, trajectory optimization is not aware of what the policy can and can't do, and therefore it doesn't know how to prepare a good training set. So what we're going to have to do is we're going to have to close the loop. We're going to optimize our policy to match the trajectory distributions, and then we'll go back in and re-optimize the trajectory distributions to avoid taking actions that are too different from the policy. And by repeating these two steps in a loop, by alternating between trajectory optimization and policy optimization, these two sides of this loop will agree on the same behavior. And once they've agreed on the same behavior, then samples from the trajectory distribution are well suited for training our policy. So this kind of cycle, this is the key structure in guided policy search. This is what's going to actually make this algorithm work, alternating between trajectory optimization and policy optimization. So this is the overview of the algorithm. Now the next question to ask is this procedure actually solving some well-defined problem? Is it actually going to provide us with a good policy in the end? Can we say something about its performance at convergence? Well, what we can do is we can actually derive this guided policy search algorithm starting from the initial optimization problem that we care about, and that's the minimization of the cost under our final neural network policy. What we're going to do is we're going to rewrite this minimization as an equivalent constraint problem, where we're minimizing the cost under the trajectory distribution, subject to the constraint that the distribution of our actions under the policy and under the trajectory distribution are equal. So what this constraint is saying is that basically the policy and the trajectory distribution are going to take the same actions. So that means that they're actually the same distribution, and the cost under one is equal to the cost under another. So this constrained optimization problem is the same as our original optimization problem. And now what we're going to do is we're going to solve this constrained optimization problem using dual gradient descent and arrive at the same structure that I described on the previous slide. So what we need to do first is we need to rewrite this constraint in a form that makes it a little bit more manageable, because originally we have an infinite number of constraints, one for every state and every action. If we instead place the constraint on the KL divergence between pi and p, and say that KL divergence is equal to 0, then we'll have a finite number of constraints, one for every time step. And now we can apply dual gradient descent to solve this optimization problem. You can also use a method like Bregman ADMM, which is going to produce a slightly better result, but it's a little bit more complex to derive. So I'll go with the dual gradient descent version here. For notational shorthand, I'll rewrite this constraint like this, just so that I don't have a massive equation there. And to apply dual gradient descent, we have to write down the Lagrangian of this problem. So in the Lagrangian, we have the objective, and then we have the constraints that enter into Lagrangian multiplied by Lagrange multipliers. And dual gradient descent solves these kinds of constraint problems by alternating between minimizing the Lagrangian with respect to the primal variables, that's the trajectory distribution and the policy parameters, and taking a subgradient step on the dual variables. And it turns out that if we actually continue with this derivation, we can actually arrive at a cyclical algorithm that has very similar structure to the one on the previous slide. We're going to minimize the Lagrangian with respect to the trajectory distribution. This corresponds to trajectory optimization. We're going to minimize the Lagrangian with respect to the policy parameters, and this is simply supervised learning because the policy parameters only appear in the constraint. And then we're going to take a subgradient step on the dual variables. And this is like saying that if a constraint was violated, enforce it more strongly the next time around. And then we'll repeat this process. So on this slide, I've shown that alternating between trajectory optimization and supervised learning for the policy will actually optimize a constrained objective of this type up here, and that's equivalent to optimizing the expected cost under our neural network policy. So guided policy search really is optimizing some well-defined objective and will give us a good policy at convergence. Okay, so let's look at some results. Let's see if guided policy search can actually be used to train neural network policies that generalize in some meaningful way. What we're going to do here is we're going to optimize 4 different trajectories to recover from pushes. So in the 4 different training scenarios, there's a push that's delivered on the first time step, and then the trajectory has to recover and walk forward. There's going to be 4 pushes in different directions and at different points in the gate, and we're going to optimize a single neural network from these 4 pushes. And then we're going to test this neural network in a variety of different push scenarios to make sure that it generalizes. So at training time, there was only ever 1 push delivered on the first time step, but at test time, we can see that this network actually performs reasonably under a number of different push scenarios where multiple pushes are delivered at different points in time. Here, we're going to deliver a large number of small pushes, and you can see that the walker actually manages to remain upright. So the point here is that the neural network didn't just memorize 4 different push recoveries. It actually learned a generalizable notion of balance, which is what it needs in order to recover from all of these pushes. Now, these results were obtained in simulation, and we actually had a known model of the system dynamics so that we could perform this trajectory optimization using a standard model-based technique. For robotics, it's very valuable to be able to do policy search under unknown dynamics, because even if we can identify the dynamics of our robot, we can't necessarily identify the dynamics of every single object that that robot might ever interact with. So in the next section, I'm going to talk about how we can do that.
Can I ask a quick question?
Yes, please.
So if you go back to your optimization problem, you have both a non-convex objective and non-convex constraint.
Yes. Yes. So in general, the best we can hope for is to get a local optimum for this problem. But this is generally true for a lot of these policy search tasks because the space, the problem is always going to be non-convex.
Yeah, and I'm just trying to understand the dual piece that you did there and what effect that has. Because you're basically putting the, let's say, the KL constraint into the objective function. That's what you're doing. So you're finding local optima of the Lagrangian. I see.
Yeah. Yeah, and there's a more sophisticated version of this using Bregman ADMM that I can discuss with you offline. That's maybe a little bit more interesting in this regard. Okay, so as I mentioned before when I talked about this maximum entropy optimization, in order to optimize the trajectory distribution, we need to know a linearization of our system dynamics. So we basically need to know the derivative of the next state with respect to the current state in action, which ordinarily we would obtain from the equations of motion of the system. If we don't have these equations of motion, here's what we can do. Our trajectory distribution is a Gaussian distribution over trajectories. And that means that the conditional PU given x is a linear Gaussian. Conditionals in a Gaussian become a linear Gaussian. So PU given x is actually a time-varying linear Gaussian controller. We can actually run this thing on the robot. We can basically execute this trajectory and see what it does in the real physical world. We would initialize this usually at random. So what we can do is we can run PU given x on the robot and collect the data set of trajectories. And then what we can do, at every time step, we can actually fit the dynamics using linear regression. And then we can just pretend these fitted dynamics are the linearization of the system, feed that to our optimal control algorithm, and get a new and improved trajectory distribution. This is a very sensible approach, but it has one key flaw, which is that the real dynamics are, of course, going to be highly nonlinear, and that means that far away from our samples, there's going to be a big disagreement between our fitted dynamics and the true dynamics. So if the new trajectory that we optimize visits one of these regions where the dynamics disagree, and then we go and run it on the robot, it's going to do something completely crazy, and this algorithm will diverge. So the key to making this work is to actually keep the new trajectory distribution close to our samples. And the way we can do that is by solving a constraint problem where we minimize the expected cost under the new trajectory distribution subject to the constraint that the new distribution and the old one are within some small KL divergence of one another. And the step size epsilon here can actually be adjusted adaptively based on how well we're improving the objective. So if we solve this constraint problem, our new distribution will be close to the old one, and the dynamics will be reasonably valid. And then we can repeat this process, take more samples, update our dynamics, optimize the distribution, and so on. Now, these trajectories tau that we sampled by running the controller on the robot are actually samples from our trajectory distribution. So they're exactly the training set we need in order to optimize our neural network policy with supervised learning. And then the neural network is added as an additional term in the cost for when we optimize the trajectory distribution, so that the trajectory distribution and the policy come into agreement. So this is...
Do you have an exploit problem in this part?
In general, yes. And one of the effects of bounding that KL divergence is that the variance of the trajectory distribution doesn't collapse too quickly, which has a kind of exploration effect, but exploration is not explicitly handled in this framework. Now, let's see if this algorithm can actually solve some interesting robotic manipulation tasks. We're going to test this method on the task of stacking Lego blocks, putting tight-fitting wooden rings on pegs, assembling a little toy airplane, putting a shoe tree into a shoe, and putting bottle caps onto bottles. First, let's look at the learning process. So here, the input to the policy consists of the joint angles of the robot and the vector from the end effector to the target, as well as their time derivatives. And the output consists of the torques at the robot's joints. So this is directly doing torque control. At the initialization, the motion is completely random. And as the learning progresses, you can see that the robot gets closer and closer to the target. You might have figured out already where the target is. This training procedure takes 10 minutes of real time, of which 3 is spent actually running the controller on the real system, 3 is spent on computation, and 4 minutes is wasted because we implemented this in MATLAB and we didn't do a very good job. So since then, we actually coded this up properly, and it actually takes only 5 minutes. The computation time is a little shorter, and there's no wasted time. So let's look at what the learned controllers actually look like in the end. Here's the Lego block controller for a different target position. Here, the Lego block is freestanding, which offers an additional challenge because it can get pushed out of the way. Now, the thing to note about these motions is that they're quite fast and they're very fluid. So if you've seen videos of robotic manipulation before, you might have noticed that often these videos are sped up. This is actually not sped up. This is in real time. And the reason that it's fast is because the controller is actually optimized on the real physical system. For the airplane task, you can see that the wheels have a round peg and then a rectangular base with a little notch in it. And that notch has to be aligned properly for this task to succeed. Here's the shoe tree task. And for the bottle cap task, which you'll see next, we do actually tell the robot to spin the wrist, but otherwise it has to figure out on its own that it has to spin the wrist and push down at the same time to get the bottle cap into position. And now for all of these behaviors, we do actually give it the position of the target, so it's just trying to put the object in the right configuration and perform whatever motion is necessary to do that. Here are the learning curves for this task. You can see that for all the behaviors I showed, they were learned with between 20 and 30 samples, so each sample is one motion. This is much faster than what you would get with a standard reinforcement learning method, which would typically require on the order of hundreds of samples for a task like this. Now, can we actually use this method to learn some neural network controllers that will actually generalize in some non-trivial way? To answer this question, we trained neural network controllers that can place the Lego block and the ring at a commanded position. So the training was done on the position shown in red, so there were 4 training trajectories for each case, and then we tested this neural network on the positions shown in green. And this network has 3,500 parameters. And here's how it performs on the test positions. And you can see that for each test position, the controller actually successfully gets the block in the right place. Now again, here we do give it the target position as input. In general, if we want to learn interesting sensory motor skills, yes?
How deep is the network?
Here it's 2 layers. So in general, if we want to learn sensory motor skills, it helps to be able to deal with rich sensory input. So that's going to be the objective in the next project that I'm going to discuss, where instead of feeding the target position directly to the controller, we're actually going to give it images as input, and we'll have to figure out by itself where the target is. So here the network is going to be substantially more complex. Here we're going to learn to do perception and control together, which will allow the perception layers to actually adapt to the goal of the task and avoid the kinds of errors that are most harmful for task performance. The policy representation here is a convolutional neural network, which is a very popular class of models in computer vision, but is not very popular for robotic control because these models are so high-dimensional. They're very difficult to optimize with standard reinforcement learning. We're going to begin with an image that's arranged in 3 color channels, and we're going to process that image with 3 convolutional layers. Each of these convolutional layers, you can think of it as an image. It's called a response map. And we're going to, at every point in that image, process a filter. And this filter takes as input a receptive field lying underneath that point. It applies a linear transformation followed by a nonlinearity to compute the activation at that point in the response map. The same filter is applied at every point in the response map, and there are 64 filters in the first layer. And then the next convolutional layer is constructed analogously using the preceding layer as input. So these 3 convolutional layers learn a hierarchy of visual features. Now these visual features are then arranged in a pixel-wise fashion into these response maps. For doing motor control, it really helps to have a spatial representation of the task, things like Cartesian coordinates. So the role of the next layers is to convert this pixel-wise feature representation into a spatial representation. What we're going to do is we're going to take all of the activations at the last layer, we're going to exponentiate them, and we're going to normalize. So this operation, the softmax operation, serves to suppress non-maximal activations, which is a kind of lateral inhibition effect. So it kind of suppresses those activations that are erroneous, that are not as strong as the strongest activation in the image, which improves the robustness of the network. And it constructs a probability distribution over positions in the image. And now what we're going to do is we're going to take the expected position of the peak in this image. And that's done by pointwise multiplying every point by its 2D coordinate and adding these together. And that gets us one 2D coordinate per channel. So there's 32 of these points total, and we can actually visualize them, and I'll analyze this a little bit more later. So this is the representation that's actually fed into the motor control layers, which are going to then choose the torques to apply on the robot's joints. So this is the model. Now, how can we train this model? Well, this is technically a partially observed task, because there's some state about the world that the robot doesn't get as input, but has to figure out from the images. For example, in this task, where the robot is learning to put that red shape into the shape-sorting cube, the unobserved portion of the state is the position of the target. It has to be inferred from the image. In guided policy search, we need to solve the problem with trajectory optimization before we can train the neural network policy. So we're going to use an instrumented training setup. For training, we're going to instrument the training environment so that we can measure the full state of the system at training time. For example, in the case of this shape-sorting cube, we're going to hold the cube in the robot's left gripper so that we always know where it is. We're going to use that full state to optimize the trajectories using the method I described in the previous section, but then we'll hide the full state information from the policy and only give it input from the robot's camera. So that will force the policy to learn how to see, so that at test time, it can actually succeed at this task without the instrumentation, without needing to hold the object in its left gripper, for example. So this instrumented training setup is a very practical way to learn these kinds of partially observed tasks that's going to be substantially faster than actually trying to tackle the partial observability head-on. Now, at this point, we can apply guided policy search to train these visuomotor policies end-to-end to do both perception and control. However, this would take quite some time, because in the inner loop of guided policy search, we're actually doing supervised learning on this convolutional neural network, which has a large number of parameters. However, we can reduce the number of iterations dramatically by appropriately initializing the policy. And the way we're going to do this initialization is by having a pre-training phase where the robot basically moves the target object through a range of different positions. The robot is kind of playing with this object to see what it looks like from different angles. Each time, the robot records the image and records the unobserved portion of the state from the instrumentation. And then we're going to initialize the vision layers just by solving a regression problem that maps images to the unobserved portion of the state, like the target position. And this will initialize the vision layers with some reasonable initial features that will get it started towards policy learning. The trajectories are also initialized by using the method in the previous section. So instead of initializing the trajectories to be completely random, we'll initialize them so that they roughly go to the target by running that trajectory optimization method that I described before. And now with these initializations, we're ready to run guided policy search for about 4 to 5 iterations to optimize the visuomotor policy end-to-end to do both perception and control. So let's see if this method can actually be used to solve some interesting robotic manipulation tasks. We're going to test it on inserting a trapezoid into a shape-sorting cube where there's only a few millimeters of tolerance, putting a coat hanger on a rack where the robot needs to determine the distance to the rack from monocular images, fitting the claw of a toy hammer under a nail where the hammer can be grasped at different angles, so the robot actually has to figure out how it's holding the hammer from the image, and putting a bottle cap onto a bottle. So here's the shape-sorting cube task. As I mentioned before, at training time, the robot is actually holding the cube in its left gripper, but at test time, because the policy actually learned how to do vision, we can actually put the cube on a table, and the robot will automatically figure out where to put the shape regardless of the cube's position. Here's the coat hanger task. At training time, the coat hanger doesn't have any clothes on, and neither does the rack. But at test time, we're actually going to put clothes on both the rack and the coat hanger to determine whether the policy can generalize to visual variation in the scene. So it was not trained with clothes in the scene, but it can actually generalize to that situation successfully. Here's the hammer task. So here, the hammer can be grasped at a variety of different angles, and you can see that depending on the grasping angle, the wrist needs to be tilted very differently for this task to succeed. And at test time, we're going to add some visual distractors to the scene to make sure that the policy actually generalizes successfully. Here's the bottle cap task. So here the setup is similar to the one in the previous section, except that now the position of the bottle is not given as input to the policy. The policy has to figure out where the bottle is on its own from looking at the images. And for the visual test, we add distractor objects into the scene again. Yes, please.
Last time you did bottle cap, it spun backwards to get the threads aligned to move forwards. This time it only went forwards. Why is that?
Oh, this time it only... You know, I'm not sure. There were also some changes to the algorithm underneath, and the bottle here is different. I actually suspect that the main difference is the shape of the bottle, because there we had these pill bottles that are a little bit more finicky. This one is a very big cap, so it has very big threads. Maybe that's why. I'm not sure, to be honest. So I mentioned before that we can visualize these feature points that are actually learned by the vision layers of the network. So here's a visualization of the feature points for the 4 tasks. The points learned after end-to-end training of the visuomotor policy are shown as blue circles, and the points that we get if we just pre-train the vision layers to predict the target position are shown as red crosses. So what this is showing is that the feature points really do change after you do end-to-end training of the visuomotor policy. The blue circles tend to cluster more on task-relevant objects in the scene, like the target object, the gripper, and the object held in the gripper. So now, here's a question that we'd like to answer. Does end-to-end training of these visuomotor policies, learning perception and control together, actually improve performance compared to training the perception layers and the control layers separately, which is the more standard approach in previous work? To answer this question, we're going to compare to two baselines. The first baseline, we're going to train the vision layers just to predict the target position. We're then going to freeze these layers, so we're not going to change them anymore, and we'll feed the target position as input to the motor control layers. So this is basically the method in the previous section, except that instead of giving the true target position to the controller, we're giving it the position that's predicted by a vision system that's trained in advance in standard supervised fashion. So this is the most similar to the standard way of doing this task. The second baseline is similar, but has a little twist in it. We're going to train the vision system in the same way, but instead of feeding the predicted target position to the motor control layers, we're going to actually feed the visual features to the motor control layers. And this gives us a little bit more flexibility. It's a slightly richer representation. So let's see how these baselines did. The post-prediction baseline, which is the most similar to previous work, achieved a 50% success rate on the coat hanger task and very rarely succeeded on the shape sorting cube and the toy hammer task. We didn't get a chance to test it on the bottle task. The post-features baseline achieved a higher success rate, but the end-to-end trained visuomotor policy achieved by far the best success rate on all of these tasks. So what's going on here? In particular, why is the post-prediction baseline, which is using the vision system to predict the position of the target, performing so poorly? Well, we looked at the accuracy of the post-prediction, and we tested a number of different architectures, and we, of course, chose the best one, which on average achieved 1.3 centimeters of error. This roughly agrees with previous work. This is a paper from Willow Garage that reported an error of 2 centimeters in localizing an object using a checkerboard. But the shape sorting cube task has only a few millimeters of tolerance. So this kind of accuracy is simply not good enough for a task like this. And this means that training the visuomotor policy end-to-end to do both perception and control actually improved the accuracy of the final policy. And this is getting at some of the ideas that I used to motivate this talk in the beginning, where learning a tight coupling between perception and control actually produces a more robust and more reliable control strategy. OK, let's look at a few more results. Here I'm going to show the input to the policy as an inset, so that little square inset is actually what the robot is seeing. You can see that the coat hanger generalizes to a wooden coat hanger. It was trained on plastic coat hanger, but generalized to the wooden one. Here we're adding distractor objects into the scene to make sure that the policy is robust to visual variation. Here we're actually holding the object. And initially we tried the green glove because we thought we might need it, but it turns out to work just fine without it. Yes?
Is the pose of the object in the grippers is very similar between the different trials, right?
For the shape sorting cube, yes. For the hammer, we intentionally varied the grasp to force the robot to learn how to orient its wrist in response to the image. Yes. So in that last one I showed you, you could see that I was actually pulling the bench out of the way to make sure the policy follows. Here's another fun experiment. This is a kind of perturbation test. You can see that the policy is very compliant, so when I push it out of the way, it actually attempts to recover. Now, the policies that I showed here, you can think of them as kind of instance-level policies. They're trained on a particular bottle to put a cap on a particular kind of bottle, and they'll succeed on that bottle, but in general, there's nothing to guarantee that they'll successfully generalize to all the other bottles in existence. In general, if we want to learn highly generalizable sensory-motor skills, we need to do something more. And that's what I'm going to discuss for future work. To start thinking about generalization, let's begin by thinking by analogy to supervised learning. There have been a lot of success in supervised learning in recent years, and these successes have three key ingredients behind them: the availability of large amounts of computation, improvements in algorithms and models, and the availability of large amounts of data. And this third point cannot be understated. In fact, many of the most important improvements in algorithms and models have been those that have enabled learning rich models that can effectively make use of large amounts of data to recover interesting patterns. So where are we at with learning sensory-motor skills? Well, we have access to the same kind of computational power. The algorithms and models are perhaps not as far along, although perhaps some of the methods I described in this talk bring us a little bit closer. But in the end, there's no way to get around the question of data. If we want to learn highly generalizable sensory-motor skills, and if we want to learn large libraries of sensory-motor skills, we're going to need to get a lot of data. And if we can get a lot of data, then we can learn large repertoires of motor skills for robots so that they can do chores in the household, or we can learn highly generalizable sensory-motor skills so that we can have robots for disaster relief scenarios, going into unfamiliar environments, and reacting intelligently to unexpected events. So where can we get data? We can get data for learning sensory motor skills from experience, like I described in this talk. We can get it from demonstrations. We can get it from shared experience of other robots. And we can get it from other prior data sets, like data sets of images and 3D models. So in regard to learning from demonstration, I already alluded briefly to the fact that guided policy search can actually use demonstrations to a limited degree for initialization. And this is how this 3D running result was obtained. In my own previous work, I've used learning from demonstration in the context of computer graphics. So this is a martial arts character animation system that used motion capture of humans and then a combination of nonlinear embedding and reinforcement learning to learn controllers that actually react to a moving target in this case. Here's an example from robotics from my own previous work. First, I'm going to show a little baseline. Here we have the kinematics of a single demonstration, and we're just transferring those kinematics to a new towel. So the goal here is to fold this towel. But if we just transfer the kinematics of a single motion, it doesn't capture the essential property of this task, which is that sometimes you need to pull the towel to get it taut, and sometimes you need to position your grippers very precisely to grasp the towel. If we analyze multiple demonstrations, we can actually determine automatically when should we apply force and when should we position the grippers very precisely. So here we're actually learning a variable impedance controller from multiple demonstrations that automatically learns when to position the grippers very precisely to grasp the corners and when to pull on the edges of the towel to get it taut. Now, going forward, we can actually get a lot more from demonstrations than just initialization of trajectories or when to apply force. We can actually analyze demonstrations to determine the goal of the task. So in a lot of the manipulation skills that I showed, the goal was very simple. It consisted of getting a particular object to a particular place while minimizing torque. But what is the goal for folding a towel? Well, this is a very difficult question, actually, because there aren't even sensors in the towel that tell us whether it's well folded. There are no sensors that tell us whether there are wrinkles. Pretty much the only way we can tell if the towel was folded successfully is by processing input from vision. On the other hand, it's quite easy for me to demonstrate the towel folding behavior myself. So it would be really nice if we can acquire this cost function from demonstrations. Learning cost functions from demonstrations is called inverse reinforcement learning. And the key challenge in inverse reinforcement learning is to learn cost functions that have the right structure, that will actually capture what it means for the task to succeed. In my previous work, I've developed algorithms for inverse reinforcement learning for high-dimensional and continuous tasks that traditionally pose a big challenge for such algorithms. And in future work, I'm looking forward to developing methods that will combine inverse reinforcement learning with deep learning to learn cost functions from images. If we can do this, then we can acquire cost functions for tasks like towel folding, but we can actually do a lot more than that, because the cost function decouples the task from the physical system. And that means that we can learn the cost function from a human doing a task and then optimize that cost with a robot. And if we can do that, then now we suddenly have access to very large repositories of data on the internet. We can look up videos of humans doing interesting behaviors, recover cost functions, goals, and sub-goals, and optimize those goals and sub-goals on the robot to perform a wide range of different tasks. Now, besides learning from humans, robots can also learn from other robots. For example, we might imagine a number of different robots deployed in different factories that are engaged in packing boxes. They're all packing different boxes, packing different things into those boxes. But if they can share their experience and learn a single sensory motor skill for box packing, they can improve the performance of each individual robot, and they can learn a generalizable version of this skill so that when a robot is placed in a new situation and asked to pack a box, it'll immediately know how to do this. Now, the key challenge here is not so much how to learn from multiple robots directly, but how to learn opportunistically. Because it's impractical to say that we're going to buy 20, 30 different robots just to learn how to pack boxes. What we'd really like to do is learn from a number of different robots that are deployed in different situations, perhaps owned by different people in different companies, that are doing their own thing. And to do that, we have to learn opportunistically. Guided policy search offers us a starting point because guided policy search already combines multiple trajectory distributions into a single policy. So each of those trajectory distributions might be running on a different robot. But there are still a number of very important challenges to tackle. First of all, each of the robots might be executing a different policy, not just this linear Gaussian thing. It might be running a neural network. It might be running some other policy. So we have to deal with heterogeneous policies on the left side of this picture. We have to deal with asynchronous learning because we can't ask all of these robots to take one iteration, then wait a little bit while we do some computation, then run again. They're all doing their own thing, so we have to learn asynchronously. We have to learn on their time, not on ours. And we have to learn in an unobtrusive way. So if we're going to modify the behavior that these robots are executing, we have to offer some kind of promise or some kind of guarantee to the owner of these machines that we're not going to modify their behavior in a way that adversely affects the particular instance of the problem that robot is trying to solve. But if we can overcome this challenge, then again, we can get access to a very large amount of data. We can get shared experience from multiple robots doing similar tasks and learn a highly generalizable representation of that behavior. So I talked about how we can learn from experience, how we can learn from robotic demonstrations, human demonstrations. We can also learn from prior data sets. For example, if we're trying to learn how to put bottle caps on all bottles in existence, if the physics of this task is very similar and only the appearance of the bottle changes, it seems like we shouldn't have to touch 100 different bottles. It should be enough to just learn how to put one cap on one bottle and then see images of what different bottles look like to figure out how to generalize. So in the framework of guided policy search, prior experience and demonstrations enter into the left side of the cycle. Prior data is going to enter into the right side. I've already alluded to how this can be done when I discussed the pre-training procedure for the visuomotor policies, where I initialized the vision layers of the policy by pre-training on predicting the target position from the images. In general, the policy is optimized with supervised learning. We can think of these prior data sets as partially labeled training instances. So samples from our trajectory distributions contain images and the commanded torque. Prior data sets just contain images. They're partially labeled training instances. Incorporating partially labeled training instances is called semi-supervised learning. And semi-supervised learning is a very active area of research right now in machine learning because of the promise of incorporating unlabeled data. And I think it's going to make an even bigger difference for learning sensory motor skills, and this is an area that I'm very interested in exploring in the future. Now, in addition to robotic control, I think some of these ideas for policy search also have implications for broader applications. First, I'm going to give you a few examples from my prior work, and then I'm going to discuss some ideas for future work that I'm very excited about. So one of the examples is a project that I worked on with collaborators here at the University of Washington, in particular Travis Mandel, who's sitting right there. And here the goal was to learn an adaptive policy for concept ordering in an educational game. So here we had data from players playing this game to teach them fractions, and this data was analyzed to learn an adaptive policy that looked at what the player was doing and chose the next concept to show to the player. And this method was able to obtain a 32% improvement in the number of concepts that were completed by the player on a large-scale trial with 2,000 students. Here's another example from my previous work. This is a computer animation example. Here, the user is speaking into a microphone, and the character is automatically animated with hand gestures that are suitable for the speech. Here, there's a probabilistic model that was trained on data of motion capture with audio to predict the gestural style based on the speech, and then reinforcement learning was actually used to build a controller that chooses the most suitable gesture based on the inferred gestural style and on the preceding gesture in order to create a smooth animation. In future work, there are a number of directions that I'm very interested in exploring in collaboration with domain experts in those fields, such as autonomous vehicle control. In fact, I'm already looking at ways to design architectures for visuomotor policies for tasks like high-performance flight. I think biomechanics is a very interesting application area. If we can learn realistic human-like motor skills, then we can do predictive simulation in biomechanics. We can, for example, predict how somebody's gait might change when they're carrying a heavy load or after a surgery. And I think in the domain of vision and perception, we can use some of these ideas for end-to-end training of visuomotor policies to move towards goal-driven perception, where the perception task involves an active component, perhaps an active perception component, or is optimized for a particular goal rather than something abstract like misclassification error. And perhaps a more mundane point here is that some of the techniques that we develop for end-to-end training of visuomotor policies, components like this transformation for spatial features, can be used in computer vision. In fact, I'm already working to apply this particular technique for a pose estimation task in computer vision in collaboration with computer vision researchers at Berkeley. Okay, I'd like to acknowledge my PhD advisor, Vladimir Colton, as well as my postdoc supervisor, Pieter Abbeel, my collaborators at UC Berkeley, Stanford, here at the University of Washington, at Carnegie Mellon, and at Adobe. Here's a bibliography of the papers that I've discussed, and I'd be happy to take any questions. We have a question over here.
So the other example I know of deep reinforcement learning is the folks at DeepMind. Mm-hmm. And in their case, they say that the way they got the reinforcement learning to work was by doing experience replay. Mm-hmm. But you apparently didn't need that here because what you need out of the vision system is much more constrained. It's just the location of the...
So yeah, I can say a little bit about that. There's a very big difference in the setup between that setup and what I'm doing. Because in the DeepMind system, the key there is that there's a very large amount of experience available because the experience is collected in simulation. It's actually days and days and days of video game playing experience. This is unfortunately not something that we can do in a robotics setting because every piece of data on the robot sort of comes at a high price for us. If we can't just run this robot unattended for days. So that's really the main difference. In regard to experience replay, that's actually very similar to what's going on here. It's basically a batch setting. So this is also a batch setting. So that's actually not that different. The main difference is the volume of data that's collected. Here it's dramatically less.
But that would make your problem harder, and therefore you're less likely to succeed. So
sorry, what would make it harder?
Yes, you have a lot less data, right?
Right. Yes. That's what I'm saying. This is a more difficult problem in a lot of ways because there's a lot less data. Well, in fact, many orders of magnitude less, in fact.
Right. So if it's a much more difficult problem and yet what you're doing is similar, how come you're still succeeding?
Well, so the key to the success is that I'm not trying to optimize the policy directly. So they're trying to optimize the policy directly from the experience. I'm actually decomposing the policy search task into two parts, the optimal control part and the supervised optimization for the policy. And optimal control offers much more sophisticated tools for actually optimizing the robot's behavior. And that's really the main idea here.
Maybe I can sneak in and ask a question.
Yes, please.
So you showed very convincingly that doing random things on a biped is a bad idea because you get bipedal falling. But then you move to the robot and you say, okay, we don't know the physics, so we're going to happily sample from the dynamics and see what happens. Mm-hmm. How do these things work together? I mean, the PR2 is not a bipedal robot; it's not going to fall. But
so the initial motion of the robot is not completely random, in that we're not choosing a random real-valued number. It's actually Gaussian noise with zero mean and a little bit of feedback to just keep it at the initial state, which is just the built-in PD control. So you do need some reasonable initialization, but that initialization is not task-specific. It's just something that keeps the system from hurting itself, some kind of reasonable kind of state-holding thing. Yes?
So when can I actually buy this from Walmart so I can clean the house?
Yes. So that's an interesting and quite difficult question. So I think that going from the instance level, going from the point where we can put a cap on one bottle to the class level where we can put caps on all bottles in existence, this kind of scaling, that needs to happen first. And the scaling is going to be kind of the next step in this work, figuring out how to learn from large amounts of data, how to get large amounts of data so that we can train a robot, for example, in a lab environment, and it can go and succeed at various tasks in your home. So that level of generalization is not quite there yet, and that's the next step. Once that's in place, then things are going to be a lot more straightforward. But I should say that this is actually a very good time, in my opinion, to be looking at these kinds of problems because we're actually seeing now that robotics is moving into the realm where robots are becoming affordable. Even manipulating robots are now approaching the point where you can buy a Baxter for $20,000, and this cost is going down rapidly. So the robot that I showed here, the PR2, it costs about on the order of $500,000. The Baxter costs $20,000, so that's already more than a tenfold reduction. And we can expect further reduction in the future, I think.
Do you have any experience working on kind of visually dissimilar tasks, but it's the same task? So for instance, screwing in the bottle cap or screwing in a screw?
Yeah, so this is actually something that, just to repeat the question was, do I have experience on looking at tasks that are physically similar but visually dissimilar? This is actually something that we're looking at right now. So one of the first steps towards generalization is to look at to have the robot simultaneously learn to do tasks that are a little bit different but related in some structural way. Right now we're actually looking at, we have this little toy screwdriver. And we're playing with a toy screwdriver and the bottle cap. That's one. And the other one is for the shape sorting cube. We're looking at putting different shapes into the shape sorting cube. So the results here were just for the red trapezoid, but we're also looking at kind of all the different shapes that we can put in to see if the policy will generalize.
So when you constructed the visuomotor transformation, you, by hand, collapsed everything down into a 2D to 1D problem, the end effector position and the XY coordinate of the peak of the output of the visual deep band. Right?
I wouldn't say it's 2D to 1D. It's really, the image is, it's 240 by 240, so it's very high dimensional. It's from that to 2D.
Then it goes down to 2D, and then it goes into the network. So what are the challenges when you start scaling up the dimensionality of the ins and outs of that second?
Well, so I should say, by the way, it's not just one 2D point. It's a number of points. And the number of points is basically your number of features. The reason for this transformation is because, as I mentioned in response to Pedro's question, data here is very limited. So we'd like to set up the network in such a way that we're giving it good inductive biases. And the inductive bias that's provided by this transformation is that images are homogeneous in the sense that the top left corner of the image is not in any way structurally different from the bottom right corner, that pixels are all pixels. And the representation that we care about is going to have a spatial character to it. So that's the knowledge that we're encoding in this network, and that's what lets us avoid learning a very big, fully connected layer from the last convolutional layer to the first fully connected layer. So that saves us a huge number of parameters and dramatically reduces overfitting. So that's the role of that component. I think when it comes to scaling it up, I don't think it's a huge problem because we can simply increase the width, the depth of that layer and basically add more features. So that's actually not a big problem.
So you're not afraid of not having enough data at that training step?
No, because this step is actually more data efficient than if you were to put a big fully connected layer there because it has fewer parameters.
Sergey, let me ask you one more question. So going from a $500,000 to a $20,000 robot, there's a reason why the Peer 2 costs $500,000, right? It's a much better robot. So would this work on a crappy robot like Baxter?
It already does. So actually, just before this talk, I got an email from a student I'm working with who told me that he had the linear Gaussian controllers running on the Baxter about 2 weeks ago. Now he has the neural network running on the Baxter. So that's actually already in place.
OK, well, if there are no more questions, let's thank Sergey one more time.